The cooling device for the mid-infrared instrument, MIRI, is one of the James Webb Space Telescope's 4 instruments. The mid-infrared instrument requires a lower operating temperature than Webb's other instruments. The cryocooler accommodates this requirement. So, in this video, we will talk about the James Webb's cooling system. On May 24, MidInfrared Instruments cooler officially passed its pre-ship review. Its main portion, called the cryocooler compressor assembly, was shipped on May 26 to its next destination, the Northrop Grumman Aerospace Systems facility in Redondo Beach, California. There, the cooler will be united with the body of the Webb spacecraft. The mid-infrared instrument itself is currently at NASA's Goddard Space Flight Center in Greenbelt, Maryland, where it is part of the Integrated Telescope and Instruments. Eventually, those components will make their way to Northrop Grumman too, where the whole observatory will come together in preparation for its momentous 2018 launch. Mid-infrared instrument is a joint project of Europe and the United States, with the US portion being managed by JPL. The mid-infrared instrument cooler was developed by Northrop Grumman, and then later sent to JPL for testing to demonstrate its performance and verify its readiness for spaceflight. The Webb telescope mission itself is managed by NASA Goddard. Mid-infrared instrument will be the coldest instrument on board the telescope, operating at beyond frostbite temperatures of no more than 6.7 degrees above absolute zero, or minus 448 degrees Fahrenheit. Why so cold? Mid-infrared instrument sees what is known as mid-infrared light, which is given off by objects at around room temperature. Desks, people, and the air we breathe, for example, are aglow with mid-infrared light that we can't see with our eyes. Specialized instruments like mid-infrared instrument are designed to pick up this mid-infrared glow, but they must be chilled to avoid background infrared light that can drown out what astronomers want to see. Other infrared telescopes, such as NASA's Spitzer Space Telescope and Wide Field Infrared Survey Telescope, which is known as WISE, use thermos bottle-like coolers filled with coolants, such as liquid helium and solid hydrogen, to chill their instruments. But those systems can be large and heavier to launch. Their biggest downside is that they have finite lifetimes, warming up when their coolants run out. Mid-infrared instrument started out with a design like this but was later changed to an active cooling system, which works more like a common refrigerator. The mid-infrared instrument cooler, also called a cryocooler, can chill the instrument without the need for a consumable coolant. Engineering challenge. Being an exquisitely sensitive infrared astronomical observatory, the James Webb Space Telescope's optics and scientific instruments need to be cold to suppress infrared background noise. Moreover, the detectors inside each scientific instrument, that convert infrared light signals into electrical signals for processing into images, need to be cold to work just right. Typically, the longer the wavelength of infrared light, the colder the detector needs to be to do this conversion, while also limiting the generation of random noise electrons. Now, we will talk about the cryocooler's active cooling and passive cooling. Passive cooling. 3 of Webb's 4 scientific instruments see both the reddest of visible light as well as near-infrared light, such as light with wavelengths from 0.6 microns to 5 microns. These instruments have detectors formulated with mercury-cadmium telluride, which work ideally for Webb at 37 Kelvin. We can get them this cold in space passively, simply by virtue of Webb's design, which includes a tennis court-sized sun shield. Active cooling. The basic principle of active cooling is to compress a gas, then let it expand, a process that cools the gas. The same thing happens in refrigerators and air conditioners, which are heat pumps that move heat from a colder place to a warmer place, in reverse of what occurs naturally. A gas or refrigerant is compressed by a pump, then allowed to expand where you want the cooling to happen. The process of expansion absorbs heat, and the expanded gas is pumped away and its absorbed heat is dumped away by a radiator. The gas is then recycled and recompressed and the process begins anew. Active cooling on the Webb telescope is much more complicated than a household refrigerator. However, Webb's fourth scientific instrument, the mid-infrared instrument, or MIRI, sees mid-infrared light at wavelengths from 5 to 28 microns. By necessity, mid-infrared instruments detectors are a different formulation, arsenic-doped silicon, which needs to be at a temperature of less than 7 Kelvin to operate properly. This temperature is not possible on Webb by passive means alone, so Webb carries a cryocooler that is dedicated to cooling mid-infrared instruments detectors. Cryocooler advancements. Webb's cryocooler has advanced the state-of-the-art in spaceflight cryocoolers of this power and temperature class in two ways. The first one is the precooler uses 3 stages of pulse tube cooling versus heritage systems that have only 2 stages, and the second one is the separation between the precooler and the JT cooling hardware. Typically the separation is centimeters, not several meters. Low vibration. Moreover, one of the cryocooler's most challenging requirements is low vibration. Vibration levels need to be very low to preclude jitter of the optics and resultant blurred images. The pulse tube cooling in the precooler in the CCA and the Joule-Thomson effect cooling in the CHA has no moving parts. The only moving parts in the cryocooler are the two 2-cylinder horizontally opposed piston pumps in the CCA, and by having horizontally opposed pistons that are finely balanced and tuned and move in virtually perfect opposition. To avoid excess heat and vibrations affecting MIRI, the Webb telescope's designers had to place the majority of the cooler behind the telescope's massive sun shield. Webb's telescope and main instrument module are protected from the heat of the sun by a shade about as big as a tennis court. With the pumping portion of the cooler on the other side of the shield, a pair of refrigerant lines, one feed line and one return line, each roughly 1/16 of an inch in diameter, are used to connect it to mid-infrared instrument. In total, the cooling system involves roughly 67 feet worth of thin tubing that snakes delicately throughout the observatory, carrying the recirculating helium coolant. Next, we will talk about cryocooler in depth. The mid-infrared instrument cooling system has 4 stages, chilling gas down successively to lower and lower temperatures. The first 3 stages make up the majority of the cooler and take place in the cold compressor assembly, the largest portion of the cooler. That compressor, as well as its controlling electronics, recently passed cold and vibration tests at JPL. Engineers first fitted the compressor and their electronics into a special cold chamber and tested it, then they vibrated the compressor to mimic the effects of a rocket launch, and finally tested it once again in the cold chamber, checking out its full range of performance. The Webb mid-infrared instrument cryocooler is basically a sophisticated refrigerator with its pieces distributed throughout the observatory. The primary piece is the cryocooler compressor assembly, is known as CCA. It is a heat pump consisting of a precooler that generates about 1/4 watt of cooling power at about 14 Kelvin using helium gas as a working fluid, and a high-efficiency pump that circulates refrigerant, also helium gas, cooled by conduction with the precooler, to mid-infrared instrument. The precooler features a 2-cylinder horizontally opposed pump and cools helium gas using pulse tubes, which exchange heat with the regenerator acoustically. The high-efficiency pump is another 2-cylinder horizontally opposed piston device that circulates a different batch of helium gas separate from the precooler's helium. The CCA is located in the heart of the spacecraft bus, on the sun-facing warm side of the observatory, and it precools and pumps cold helium gas through plumbing to MIRI, which is roughly 10 meters away in the Integrated Science Instrument Module UGIC known as ISIM. The CCA is controlled by the Cryocooler Control Electronics Assembly, CCEA, which is a collection of electronics boxes mounted in the spacecraft bus inside the port-side equipment panel. The CCA is connected to the ISIM via the Cryocooler Tower Assembly, CTA, which is a pair of gold-plated stainless steel tubes, a feed line and a return line, each about 2 mm in diameter, held every foot or so by a series of delicate suspension assemblies, called refrigerant line supports, or RLSs, mounted to the outside of the observatory structure. The CTA connects to the final piece of the cryocooler cold head assembly, CHA, which resides in the ISIM. Within the CHA plumbing, inside a gold-plated cylinder, roughly the size and shape of a large coffee can, is a small, less than 1 mm, orifice that the cooled helium refrigerant passes through, resulting in expansion and final cooling of the helium gas down to about 6 Kelvin, care of the Joule-Thomson effect. This coldest of refrigerated helium gas passes through more than 2 mm tubing to a palm-sized copper block fastened to the backside of the MIRI detectors. This is where the target heat is exchanged, resulting in the cooling of mid-infrared instruments detectors to nominally around 6.2 Kelvin. The CHA also contains valves that allow helium to bypass the JT restriction when the observatory and mid-infrared instrument are in cool-down mode, such as shortly after launch during deployment and commissioning. The CCA, CTA, and CHA tubing are connected together with pairs of 7/16" fittings that on the outside resemble automotive hydraulic brake line connections. If you enjoyed this content, like, share and subscribe the channel. Thank you for watching.